Hi everyone, I'm Giacomo Delia, PhD student of the MEGVI, the Vibration Resource Group of Professor Mucchi at the University of Ferrara. I'm here in the laboratory of the engineering department for recording 3 different videos in which I will show you 3 different experimental activities. The first one, that actually is the subject of this recording, is an experimental modal analysis carried out on a chassis of a car by exploiting an electrodynamic shaker. The second video instead will be another experimental modal analysis, but on a wheel rim, but performed by using an instrumented hammer, and therefore we're gonna talk about impact testing analysis. The last video instead will be on multi-axial environmental control testing, and we will see 3 different vibration control techniques by using our 3-axial electrodynamic shaker. So let's start with the first experimental activity that I said before is an experimental modal analysis on a chassis of a car. This is our structure. That is an old project for the Formula Student competition, and we will perform the analysis by exploiting this electrodynamic shaker that you can see here. This is a modal shaker by the modal shop of 220 Newton. I said modal shaker because this is a shaker suitable for performing modal analysis. The main characteristic is the through-hole armature that allow the stinger to go up and down inside the shaker, and it simplifies the setup for the analysis. I just mentioned the stinger, that is this element here. I can take one. This is the stinger, okay? The stinger is the element that connects the shaker to the structure, and it plays a crucial role for a good modal analysis. Because try to imagine that you directly connect your shaker to your structure. In this case, you probably introduce the dynamic effect of your shaker into the dynamic of your structure, and therefore you could compromise your result, and you could alter the frequency, the FRF of your structure. So basically the stinger, the rule of the stinger is to decouple the shaker from the structure and to apply just the axial force, avoiding any side load. So therefore the stinger is designed to be rigid along the axial force and along the axial direction, and flexible along the lateral direction. Okay, the length of the stinger is important too, because if the stinger is too long, insufficient force will be transmitted to your structure, probably without covering the entire frequency range. Instead, if the stinger is too short, the structure will be less decoupled from your shaker, and you could introduce the dynamic of your shaker into the dynamic of your structure, and therefore the stinger is set up to be as long as possible to maintain lateral flexibility, but still short enough for to transmit the axial force without backing. An easy way to determine the right position of the stinger and the correct length of your stinger is to make several runs by varying the length of the stinger, and try to observe the change in the measurement. Okay, we already spoken about the structure, the shaker, the stinger. I I just say that the stinger connects the structure, the shaker to the structure, but it's not totally true, because between the stinger and the structures there is another important element, that is this one, that is the impedance head. The impedance head is a transducer that can measure force and acceleration at the same time. And as you know, this measurement is very important, because for estimating the correct FRF during a modal analysis, you must measure the driving point. And in our case, the driving point is the point that connects the shaker to our structure. And you can do that by using, thanks to the impedance head, that measures force and acceleration at the same time in the same position. You must know that the impedance head measure the force and acceleration along the actual direction of the stinger, so along the actual direction of the shaker. Okay, so just the last thing about the shaker. As you can see, the shaker is oriented with a specific angle with respect to the principal direction of our structure, so the vertical, longitudinal and transversal. Because we want to perform the analysis with just one shaker, but we must be capable of exciting all the possible mode of our structure, and therefore the shaker should be oriented in the proper configuration that guarantees to excite all the principal direction of our structure. So you can do that by using the trunnion, that is this U-shaped support here in blue. If you unscrew this handle, you can turn and move the shaker in the proper configuration. Okay, basically for this analysis we will use just one shaker, but in some cases, if you have a large structure or a heavy structure, just one shaker for performing the analysis is not enough. So you can use more than one shaker. I mean, one shaker for exciting the vertical direction and another one for exciting the transversal and longitudinal one. Or why not one shaker for each direction. Anyway, if you use more than one shaker, of course the setup is more complicated, and you must be clear that your shaker, so the input into your structure, are decorrelated during the analysis, because if during the analysis, if your shaker result to be correlated at some frequencies, you could not estimate the correct FRF, and you probably obtain false mode shapes and make big mistakes. Okay, now let me show you the remaining test equipment. We got a PC here where there is installed SimCenter Test Lab. SimCenter Test Lab is the software that we will use for this analysis. Is made by Siemens, that actually is the world leader for providing hardware and software for vibration analysis. There are several solutions and several software environment inside the SimCenter Test Lab. For this analysis, we're going to use spectral testing. That is one of the many possible software packages suitable for driving our shaker. Anyway, I will explain you in detail the software in the following. The computer is connected with an Ethernet cable right here with the SCADAs. The SCADAs is the data acquisition hardware, always made by Siemens, As you can see, the SCADAS is made up of several cards, the so-called module, that you can remove and change depending on the sensor that you are acquiring or the activity that you want to perform. There are several cables connected with the SCADAS. In particular, this BMC cable here is the one that connects the SCADAS to the amplifier. The amplifier is therefore connected with our shaker. So in our case, the measurement chain is from the computer. We decide the way by which we want to drive the shaker, so with a random profile, sine profile, burst random profile, and so on. The computer talks with the SCADAS that convert and send the signal to our amplifier. The amplifier, depending on the gain that we have imposed, correct and send the input voltage to the shaker. Therefore, the shaker excites the structure that starts to vibrate. At this point, we need some sensor that can measure the dynamic of our structure, and to do that we will use a set of 3 axial accelerometers. This is a 3 axial accelerometer, you can see. Of course, a 3 axial accelerometer can measure the accelerations along 3 directions simultaneously. And as you can see on top of the faces of the accelerometer, there are some markers, X, Y, and Z, that say to you along which direction the acceleration can be measured, and say to you the local coordinate system of your accelerometer. Each accelerometer has its own cable, okay, that ends with 3 different outputs, one for each direction of measurement, and you can connect your accelerometer to the SCADAS, right there. So first the X, okay, then the Y direction, and then the Z, okay. Then you have to fix your accelerometer in the structure, on the structure, and to do that you can use okay, if the structure have the treated base, you can directly screw it on the structure, but in most of the case you have to use some glue for paste it. You can use, for instance, super attack. In our case, we're gonna use the wax. So you can take the wax like this, okay, some wax. You can shape it with your hand and you can paste it, okay. The wax, with respect to the super attack, of course it is easier and faster because you can remove your accelerometer, you can paste it again very quickly, but of course has some disadvantages because of course the wax is less steady, I mean, and is not recommended for high level of acceleration or high frequency band. Okay, we have already seen everything about the test equipments, so let's start to talk about how to perform the modal analysis. The first step is to define the measuring points. Yeah, I mean, we should discretize our structure in a point grid. These points are the points where we will attach the accelerometers for measuring the responses of our structure. And therefore, the definition of this point is very important for estimating the correct FRF and for catching all the possible mode shape of our structure. Let's try to imagine if you have a local mode in your structure, I mean a mode that concerns just a specific area of your structure, and for any reason at the beginning you didn't consider a measuring point near this area, you cannot catch this local mode and you probably make a mistake. So in this case I have done the work for you. I divided the structure in 22 points. As already said, the first point here is okay because we have the impedance set that measures both force and acceleration. So we must measure all the other 21 points. Of course, if you have 21 3-axial accelerometers, you can paste them on your structure, and you can perform the analysis with just one run of your shaker. Anyway, it's not so easy to have 21 accelerometers because just imagine that one 3-axial accelerometer cost more than 1,000 euro, and moreover, if you have 21 3-axial accelerometers, your SCADAs must be capable of acquiring more than 60 channels simultaneously. Yes, in this case, our SCADAs can do that because can acquire 64 channels simultaneously, but this SCADAs is very expensive too. And yes, we have other data acquisition hardware with 8 or 16 channel at most. Therefore, for performing this analysis, we will use just 4 3-axial accelerometers, and we're gonna touch the accelerometer in the first 4 points, and we will perform the first run. Then we will move the accelerometer in other 4 points, and we will perform another run until we will measure all the 21 points. So yes, 6 runs in total. At the end, when all the runs are done, we will collect all the runs in one single file for estimating the FRF. So that's all about the introduction, about the test equipment, the sensor, and so on. I go to the computer in order to show you the test lab and all the steps for performing this analysis.
Okay, this is SimCenter Test Lab, our software for the vibration analysis. In particular, this is spectral testing. As I said before, SimCenter Test Lab offers you different environment solutions for different test applications. Here you can see all the packages suitable on Test Lab. For instance, if I go here in Test Lab Acoustic, there are all the solutions for acoustic analysis. Or if I go on Test Lab Environmental, we got MIMO random, random control, sign control, the TWR, that are all solutions for environmental control testing. We will use some of them in the last video. Now we are instead in Test Lab Structures Acquisition. We got also the impact testing, that is the solution, yes, of course, for the impact testing analysis. We will use it for performing the experimental modal analysis on the car rim in the next video. And now we are in spectral testing. So This is the main section. Just one thing, all the software packages of Test Lab have the same layout, so always you have a flowchart here in the bottom, you can see, that divides the process in different sections and worksheets that can help you and suggest you step by step all the action that you have to do for performing the analysis. So now we are in the navigator, so the main section. In the navigator you can see all the run that you have done, so all the data that you have acquired during the analysis. And in the navigator you can process your data, so you can plot them, you can of course compare them. Just for instance, you can calculate something like the RMS, the minimum value, the maximum. Okay, this is the RMS, and so on. Whatever you want, all the process you can process here all the data. So let's start with the analysis. The first step of the modal analysis is to create the geometry file. The geometry section is a tool that you have to add in for all the Test Lab environment solutions. So you go to Tools here, Add in, and click on Geometry and OK. And now you have the geometry section here at the end of the flowchart. This is the geometry file that I have previously done for you in order to better understand what the final result should be. As you can see, we should draw all the 22 points and to obtain a sort of sketch of our structure. As you can see, if I go to here to nodes, we have all the 22 nodes that are our measuring point, and here in X, Y and Z are the coordinates of each point with respect to the origin of the absolute reference frame. The choice of the position and the orientation of the absolute reference frame is up to you, is totally subjective. Of course, I advise you to choose a point that will make the analysis easier, for instance a symmetrical axis of your structure. Basically I have put the origin of the absolute reference frame here between point 2 and 3, so here in the middle, along the symmetrical axis of the car, and therefore all the points are symmetrical in pairs, so 1 and 4, 2 and 3, 5 and 6 and so on. They have the same X and Z coordinate, and the Y's of course is symmetrical with respect to the origin. Okay, so I delete all the nodes just to show you how I can do the procedure. So delete. Okay. First I put in the box name here 1 for the first node, that is our driving point, the point of the shaker. Then I have to insert the coordinate X, Y and Z. As you can see here, the measurement unit is meter. So you go on the structure and you have to measure the distance of the node 1 from the origin of the reference frame. Of course the X is 0, the Y is minus 0.18 and the Z is minus 0.18. Okay, if I click on accept table, you can see that the first node appears here in the display. The second node is symmetrical with respect to point 1, therefore I put 2, the X is 0, this is 0.18, and the Z is always minus 0.18. Okay, acceptable. And we have also the second nodes. Let's move on the third node. The X is 0, the Y is the same of 0.1, so minus 0.18, and the Z is 0, acceptable, and 0.4, that is symmetrical with respect to 0.3, so 0.18 and 0. Okay, the procedure for all the other points is the same. It's very easy. You measure the distance from the origin of the reference frame and insert the coordinates. Then if you skip to the lines worksheet here, you can connect the node by lines to make the geometry clearer. Okay, like this, for instance. Or if you want, you can add some surfaces here in the surfaces worksheet using 3 angles. Okay, like this. Or just a second, directly use quadriangles. Okay, like this. Okay, now we come back to nodes. I don't want to make you bored while I insert all the coordinates for all the points node by nodes, and therefore I show you how to directly import the file geometry. This could be useful if someone gives you the geometry file and you have just to import the geometry in your project. So you go here in the menu on the left, and you search your geometry file, okay, here, and you click on import geometry, and here we go, our geometry. So just the last thing about the geometry, if you right click here and go to modal nodes, you can show the Euler angles. As you can see, the Euler's angles define the orientation of the local coordinate system with respect to the global coordinate system. I mean, the global coordinate system is our absolute reference frame, the one of the structure, that one. Instead, the local coordinate systems are the local reference frames of each single point here, and of course, depending on the geometry of your structure, some point could be oriented in a different manner with respect to your global coordinate system. In our case, we have these 2 points, the 19 and the 20. If I go in views, okay, as you can see, due to the inclination of the roll bar, okay, we have a mismatch between the global and the 2 local coordinate system, and therefore in this case you have to measure the angle with a goniometer, for instance, and insert the Euler's angle here. So you can see here, okay, in this case we have point 19 and 20 have minus 18 and plus 18 degrees of rotation of the YZ plane, okay. Another point that need the Euler's angles is our driving point, okay, that is the point number 1, the point of the shaker. As I said before, we have oriented the shaker with specific angles in order to excite the all the principal direction of the structure with just one shaker, and therefore the local coordinate system of point 1, that is the local coordinate system of the impedance head, is rotated with respect to the global system. In this case we have 35 degree of rotation of the XY plane and minus 54 degrees of plane X and Z. It is very important that the red row here is perfectly oriented along the direction of the stinger, and therefore along the measurement direction of the impedance head, because the software, for correctly estimating the FRF, needs to know the direction of the applied force as well as the direction of the measured acceleration. Okay. So yeah, okay, about the geometry I've already said everything, I guess. So let's move on the second step of the analysis, the definition of the channel setup. This is the worksheet of the channel setup. Here you have all the possible input channel of the SCADAs, which are 56. Probably during the introduction I said 64, but I was wrong. They are 56. Sorry. Anyway, here on the on-off box, you can enable the channel that you want to use. Okay, as I said before, we're going to perform the analysis with 4 3-axial accelerometers, and therefore are 4 times 3, so 12 channels, plus we must consider 2 more channels of the impedance head, one for the measurement of the force and one for the acceleration, and therefore 14 channels in total, as you can see. If you click here on the show on button, you can show only the enabled channels, just to make clearer the page. Here in the channel group, okay, you can select vibration, acoustics, or static. In our case, vibration is okay for all the channel. In the box, in the point box instead, you should write the name of the point, and pay attention, because you should write exactly the name that you gave at the note in the geometry file. If you remember, in the geometry the notes go from 1 to 22, but for instance, if I write point 1 here, and I click accept table, now this point is called point 1, and therefore in the channel setup I should write point 1. Otherwise, I mean, during the post-processing, the algorithm cannot recognize the geometry file and the test data. So we come back to our geometry and put 1 here. Okay, so this is 1. The first 2 rows are for the impedance head, our point 1, the first channel for the force, and then the second for the acceleration, and all the other channels are our accelerometers. The channel 2, okay, we got 3 input for channel 2, because of course it is a 3-axial accelerometer, so 1 channel for each direction of measurement. The same for point 3 and for point 4 and for point 5, of course. Okay, so the direction. If you open the list here, you can see that we can insert plus x minus x plus y and so on. The direction here means the measurement direction of your sensor with respect to the local coordinate system that you have imposed in the geometry file. So just a second that I show you here the geometry to better understand. Okay. So if you look point 1 here, we have the shaker with the stinger and the impedance head. The impedance head measures force and acceleration along its actual direction, and therefore along the red arrow here. That is the z-axis of the local coordinate system, and therefore here in the channel setup we have to put plus z both for force and for the acceleration. Okay. Instead, the direction of the other point depends on the way you fix the accelerometers on the structure. For instance, if you have a look of point 2, as explained before, on top of the faces of the accelerometer there are the markers X, Y and Z that say to you which channel records in the direction out of that face. So if you look the X direction of the accelerometer, sorry, you can see that that is recording along the Y direction. Okay, the blue arrow, that is the Y direction, that is the Y direction of our global system. Okay, so we have to put plus y here, and the second instead, that is the y direction of the accelerometer, is concordant with the red row of the global coordinate system, that is the z. Okay, therefore we have to put plus z. The last input instead of point 2 is the z direction of the accelerometer, that is concordant with the x direction of our global system, and therefore we put plus x. For all the other points you have to do the same procedure, so to look the measurement direction of the accelerometer with respect to the direction of the global coordinate system, and insert it. For the just a second. Okay, for the input mode here you can choose voltage AC, voltage DC, or ICP. All our sensors are ICP, that stands for integrated circuit piezoelectric. It means sensors that incorporate micro electronics inside. In other words, they have the amplifier directly integrated and can feed themselves. For the measurement quantity here, you can choose a lot of stuff, for instance acceleration, angle, or force, length, and so on, depending of course on the sensor that you are using. In our case, the first channel is the first transducer of the impedance head. So we put force, and all the other are accelerometers, and therefore acceleration is the way. For the electrical unit here, millivolt is okay. Instead, for the actual sensitivity, you have to look on the calibration data cards that typically are provided by the manufacturer, and they are inside the box of the sensor. As an example, I put here a photo with the calibration data cards of the accelerometer in point 2. As you can see, you have different sensitivities for each channel, and therefore for each channel you have to put the right sensitivity. Okay, that's all for the channel setup. Let's move on the scope section.